Hello, good evening or good morning, whichever one we're at. My name is Dan Daly, and I'm here today to talk to you about P4 and how beneficial it can be when used to program OVS and to define the functionality that you want to put inside of the vSwitch, and how you can use vswitch.p4 to kickstart that. And this work is being done by the Intel P4 OVS team, where we're trying to take all of these different open source pieces and put them together so people can use them. Flash this up real fast. So why P4 in OVS? The main reason is information encoding. There's information that your application can express into the vSwitch, which can help the data plane implement the function that you're after. And so this information can, where you're specific about what information you need, this lets you better optimize that pipeline. You may have a table that's exact match, and an exact match table is a lot easier to implement in software and in hardware. You may have a table that is doing a longest prefix match, and some hardware have special tables to implement that. And so this information really helps you potentially optimize the pipeline that you have. And then once you have specified that pipeline, it's a lot easier to test a pipeline where you know exactly what matters there, where the set of matches and the set of actions is really specific. So you can test in a sort of constrained random way all the different interesting combinations and sort of avoid the uninteresting or unused combinations. The second thing that we want to encode that's sort of new is encoding the data path of a kernel. In OVS today, when we want to use something in the kernel, we sort of punt to it and say, I want to send this packet over a tunnel, or I want you to route this packet, or I need to send this to the contractor. And so we still want all those functions to still be there. We want to use the kernel to set all these things up, configure them, run the control plane for these, but we would like to be able to specify in P4 the entire data path from end to end. And this would enable potentially a more optimized pipeline that doesn't have to go hop in between what's happening in P4 and what's happening in the kernel. And also it enables us to be able to take that entire data path and put it into a different target. Maybe we put it into a hardware pipeline, maybe we put it into an optimized software pipeline. So the third thing we want to talk about is being able to program more. Is when we take our data plane beyond just OpenFlow, there are so many more things that we can imagine programming into that pipeline, where we could be using the vSwitch as to doing some amount of plumbing to string together a set of network functions, inline crypto, inline network processing. And so there's a lot of examples already out there coded in P4 that you could take and insert into that data path once you've made this change to make your data path P4 native. And then the last change is more about when you have this programmable platform, by making OVS just that much more programmable, what can you do with it? A lot of the P4 programs that we use today can be used to measure or to do telemetry on your network. And we can use that same information to validate the network to make sure the network is operating correctly. And with that information, we could then reprogram the network dynamically or make incremental changes to the network depending on another program that's running as a feedback loop. And so when you take all these four pieces together, you end up with a very programmable environment, and you have to say to yourself, well, what would I do with all that capability? And so I think if people are presented with this type of environment, I think that they'll find lots of really interesting use cases to make the network work better for them. So the first point I wanted to drill down into is how to be specific. So when we're more specific than what can be encoded in OpenFlow, we get these three key aspects, things that James talked about in the previous presentation, is that when we move to this control flow structure that we have in P4, it's very explicit which tables come in which order, which tables get evaluated for which types of packets. It gives us that nice sort of if this, then look in this table, else look in that table semantic that is sort of very natural in packet processing, but sort of difficult to achieve in OpenFlow. And then when we can constrain the types of matches that we have, that allows us to optimize that match condition later. And the same thing with the actions. If we can say, this table triggers an end cap of a VXLAN, decapper of VXLAN, it's a lot easier to test than to say, well, this table can, push a layer 2 or push a layer 3 header. Do you need to test the case where you push 5 layer 2 headers? These types of things. So you can just drill down to what really matters when you constrain your program in this way. And then once we've done that, the big difference between P4 and existing OVS today is there's this compiler step in the data plane, where the data plane could be made really generic like we have in OVS today, or we could optimize it for individual targets. So we could take our P4 program that we use for vSwitch and put it in a software backend. And that could be, XDP or eBPF or DPDK or in the kernel, whatever we want to do as a software target. Or we could ask our compiler to put it into some piece of hardware and say, does my hardware support this program that I want to run? And so, being specific allows us to, at that compile step, decide, does my P4 program fit in my target? Is my target capable enough of doing the things that I'm asking it to do inside the P4 program? And so instead of, offloading a software data plane, I can now take my spec, my contract of the data plane and say, I can move it from target to target, assuming that those targets can support the very specific data path that I've specified. The second thing is, OpenFlow and P4 is great, but we need to use a lot of constructs that are, part of networking, and today we use the kernel for that. You have tunnels, you have routes, you have IPSec tunnels, and for security groups, we use the connection tracking of the kernel, pretty extensively. And so, what two things that we've done to allow you to encode those inside of P4. The first one is called the portable NIC architecture, PNA. PNA is based on the portable switch architecture, which came out a couple years ago. But the key part of this architecture is that it sets up a set of sort of atomic functions that you can do in your P4 program. And they're portable, or meant to be sort of the lowest common denominator for a switch or a NIC inside of P4. And so for PNA, we've created these new constructs so that you can encode a connection tracker, or you can do encryption and decryption in line. And potentially, if you wanted to do something at a message level as opposed to a packet level, you could do these types of things in PNA with the new architecture that we've defined. And then if your target can support all those functions, the compiler is there to help you figure that out. So you can write your program and test it in a software data plane, and then try to retarget into some other backend, and the compiler will tell you, okay, I can do connection tracking, but I can't do IPSec, that type of thing. And so this allows us to encode all of those things that we rely upon to do, network virtualization or containers or whatever inside of our network. And the second thing is something that's been done for a while now, is that if there's something in the kernel that has been programmed, we can sort of snoop that over netlink and program that through into the P4 pipeline. And we use the method that is currently used in Sonic, where something happens in the kernel, and you pull that and program it through SCI. SCI is the switch abstraction interface. So SCI has all of the same kernel constructs that you have with tunnels and routes and MAC addresses, all those things. So we can use that to sort of reflect all the things that are in the kernel into the P4 pipeline. So the kernel stays preserved; it still functions as it does today, but the things that you've configured there are also now in the P4 pipeline. And so this is an example of how it can be achieved, is that you can have a P4 match action where you can match on something that's been configured through SCI, and you can have an action that points to a handle in SCI. So in this example, I'm matching on the header and the virtual port information of like which VM did this packet come from. And as a result, I can set the virtual network that it's living on. I can maybe set some tunnel metadata. And in that process, I can say encap this packet to the tunnel that's identified in SCI. And that SCI tunnel corresponds to a tunnel that's been configured through the kernel. And then once the packet is pushed into that tunnel, there may be other tables in the pipeline that were populated from the kernel that would also get applied. So when you are encapping on the tunnel, you want to also route that packet based on the kernel routing table, and you may also want to lag that packet based on the teamd state that's been set up on those physical ports, and then send the packet over the physical port that's been set up as a netdev inside the kernel. So this allows you to take your pipeline you have in your vSwitch and leverage all the same things that were in the kernel and be able to reference those in P4. So that is how you're getting the whole pipeline in that P4 description and taking the bits and pieces that are happening in the kernel and specifying them explicitly in that description. And once you have that, so now you have everything that's happening in the kernel that you want, and you have match action that you can sort of arbitrarily program in P4. We've already, with our Tofino switches, found a fairly large amount of use cases that are really interesting to program in P4. Most to do with networking, but also sort of inline functionality that you can program as the packet is moving through the system, such as congestion control, telemetry, accelerations, these types of functions. So you can take these P4 programs, some of them are open source, and start to integrate this functionality into your system. And once you get there, not just the vSwitch, but you could also be programming the entire network with this same semantic. So your control plane, your sort of logically centralized but distributed networking function, can be establishing these contracts between all the different programmable elements in the system and saying, this is the program I want you to run. It may have aspects of each of the different control apps that are running. I want you to enforce the policy or the forwarding behavior that is being established by the control plane. And while that's happening, we can be observing and measuring that network, and then taking that data and making sure that the network is correct, and then also potentially changing the network by maybe just changing something simple like the entries in the table, or maybe even changing the state in all these different control plane applications, or even saying, I want to change the P4 pipeline itself. I need a new function. I need to fix a bug. And so you use a program to evolve your program. And so this programmable platform enables a lot of new use cases where you can automate the types of things that are going inside of your network and how your networking is responding to the different types of events or scenarios that may come up. And so, and so the part of this picture that I want to talk about next is the vswitch.p4. It's the part of that runtime contract that is at the edge there, that is the vSwitch that's interconnecting what's running on that edge host. And we want to use this vswitch.p4 to encode network intent. So today with OVS, we have OpenFlow and OVS DB, and that works pretty well. But our proposal is to say, now that we have P4, we can have a more specific pipeline, and we can be really explicit about all of the different functions that are strung together to make that data plane. And so with vswitch.p4, you can really sort of start from a well-known set of functions that include all the types of things that are standard and in the kernel datapath, and all the things that you would do inside of a standard sort of OVN or Antrea pipeline. So virtual layer 2, virtual layer 3, all of the security groups and connection tracking that you need for stateful ACLs, all of those things are inside of a sort of a baseline vswitch.p4. And if you don't want that stuff, you can turn it off, or you can use that as a place to start to insert additional functionality that you want to see inside of your P4, or that you need inside of your application. And so how this comes together is you start with the vswitch.p4. You may use that as is, or you may add things to it or remove things. Compile it for your target. Could be software, could be hardware target, depends on your application. And then as that's loaded, in the runtime, you would populate the different entries in the match action as you have new ACLs or new forwarding rules that come up over time. And as an optional change, you could say, well, I want to actually change the P4 pipeline while the system is running. And so, this vswitch.p4 is an open source project, sort of similar to how we ran switch.p4 for our switches. And it's based on the same, P416 spec, and is using sort of this new P&A specification as its architecture. And so as a summary, so why change? Why replace or use instead of OpenFlow P4? Is that we can encode so many more things with P4. We can give a whole data path view of what we're programming, and that additional flexibility allows us to be multi-target. So we can program a software data plane or a hardware data plane if it's capable, and we use the compiler to be able to make that transition or be able to switch from target to target. And then to get people started and to provide sort of that baseline starting point that you would expect if you went and downloaded OVS or got it built into your kernel, vswitch.p4 provides that functionality. And then once you have that, once you have this extra flexibility and this great starting point, what will you do with that? What will you add? What are the different types of innovations will you create? Being able to have this flexibility, have this capability sort of latent inside of your network. So we'll be putting this code up on GitHub. And again, I'd like to thank the team for the development that we've been doing and the brainstorming to try to bring all of these different pieces to the community. And we're very much actively seeking partners to work on this, test it, try out different use cases, and to see how it works in real life. Thank you.